any and every distance in complex numbers will be represented by some modulus. When I first came across this profound realization in our source material, I've got to say, it completely shifted how I looked at abstract math. It's just wild because it proves these numbers aren't just floating around in the ether, right? They actually have a tangible, spatial reality.
Welcome to this explainer. Today, we're diving into something really cool, the secret geometry of algebra. We're going to take the cold, seemingly abstract world of complex algebraic equations and completely translate them into beautiful, tangible geometry. We'll literally see how numbers on a page map directly onto physical shapes, distances, and rotations.
Okay, let's dive into this. Here's our roadmap for the explainer. First up, the geometry of complex numbers. Then, stretching and rotating. Third, triangles in the plane. Fourth, the nth roots of unity. And finally, perfect symmetry in circles. Let's get right to it.
Section 1. Geometry of complex numbers and the fundamental rules that make it all work.
Think of the modulus not just as some random operation, but honestly, it's the mathematical equivalent of a measuring tape. When you see the absolute value, or modulus, of z2 minus z1, you aren't just staring at an abstract value. You're actually looking at the exact, tangible distance between two very specific points, z1 and z2, right there on the Argon plane. And this brilliantly illustrates how algebra perfectly mirrors geometric traits. Think about it. If you have 4 points making up a square, the distance between the opposite corners, the diagonals, they absolutely have to be exactly the same length. So when you see that the modulus of z1 minus z3 equals the modulus of z2 minus z4, you aren't just doing algebra. You are mathematically proving, without a doubt, that the diagonals of that square are perfectly equal.
Moving right along to Section 2, stretching and rotating vectors, or how we actually transform these things in space.
Now, to move things around, we have two vital actions, and I really want to contrast them here. If you multiply a complex number by a positive constant, let's just call it k, you're acting directly on its magnitude. If k is greater than 1, you stretch the vector. If it's less than 1, you compress it. But, and this is key, the direction stays exactly the same. On the flip side, multiplying by e to the power of I times alpha, that acts literally like a steering wheel. It doesn't stretch or shrink the vector at all. It just rotates it counterclockwise by that specific angle, alpha.
But all this begs a pretty fascinating question. What actually happens when we want to rotate and stretch a vector at the very same time? How in the world does the algebra handle both of those transformations at once?
Well, it handles it with this master formula. If you take your final vector state and divide it by your initial vector state, the result reveals the exact transformation that was applied. The ratio of their actual lengths tells you exactly how much it stretched, and that e to the power of I alpha tells you the exact angle it rotated to get there. It is a complete, perfect geometric map captured in just a single division problem. How cool is that? That brings us to Section 3, triangles in the plane, and dealing with shapes and center.
Now, what's really interesting here is how we can take these heavy, complex formulas and chunk them into simple geometric truths. If you know the 3 vertices of a triangle, z1, z2, and z3, you can find any of its exact centers. You want the centroid? Just average the 3 points. Want the incenter? Weight them by their side lengths, which are the a, b, and c values. And if you want the circumcenter, just find the exact point, let's call it z0, that is an equal, tangible distance from all 3 of those vertices.
And man, when we hit peak geometric balance with an equilateral triangle, the math just becomes beautifully simplified. Because the centroid and circumcenter perfectly coincide, the relationship between those 3 vertices locks into this rigid equation. z1 squared plus c2 squared plus z3 squared equals the sum of their pairwise products. And if you conveniently place the center of that triangle right at the origin, at 0, the math collapses into this elegant absolute. The sum of their squares simply equals 0. Let's move into Section 4, the nth roots of unity, where we really get to see some algebraic beauty.
Let's hit the reset button for a second and define this really clearly. An nth root of unity is just any complex number z that perfectly satisfies the equation z to the power of n minus 1 equals 0. Because it's an equation of degree n, there are going to be exactly n roots, and they're represented sequentially as 1, alpha, alpha squared, all the way up to alpha to the power of n minus 1.
Because these roots are mathematically flawless, they behave with absolute perfection. For instance, they form a perfect geometric progression. The fundamental root, alpha, basically acts as the multiplier, mathematically defined as e to the power of I times 2 pi divided by n.
If you add all n of these roots together, they perfectly cancel each other out to exactly 0. And if you multiply all of them together, the product is always -1 to the power of n minus 1.
I really want to emphasize this specific number for a moment, 0. Because these roots perfectly balance each other out, whenever you sum any n consecutive powers of an nth root of unity, the answer is always magically 0, every single time.
Finally, Section 5, perfect symmetry in circles and how we go about mathematically dividing the circle.
So, we really have to ask the big question here. How exactly do these abstract algebraic roots, born from that equation z to the power of n minus 1 equals 0, how do they interact with a tangible geometric circle?
Well, the crucial point is this. They aren't just numbers. The nth roots of unity will always perfectly slice a unit circle into exactly n equal geometric parts. Their moduli are always exactly 1, which anchors them firmly to the circle's edge, and they space themselves out with absolute undeniable symmetry.
Let's make this a bit more tactile by looking at the cube roots of unity, which is where n equals 3. You start at the number 1 on the unit circle. To find the next root, omega, you rotate counterclockwise, again like a steering wheel, by exactly 120 degrees, or 2 pi over 3. To find the final root, omega squared, you just rotate another 120 degrees. It's incredible. You have tangibly divided the circle into 3 perfect equal slices using nothing but pure algebra.
And because of this perfect spacing, the angle between any two roots of unity can never be just some random number. It must be an exact integral multiple of 2 pi divided by n. This really grounds the math in reality. For example, if you want two roots of unity to form a perfect 90-degree right angle, the total number of roots, n, absolutely has to be a multiple of 4. If it's not, a right angle is geometrically impossible, no exceptions.
Let's pull all of this together and look at the big picture. What is the ultimate secret hiding behind these seemingly cold, abstract equations we've been breaking down today?
The secret is that complex math isn't just a collection of numbers trapped on a piece of paper. Every single complex equation is essentially a geometric map. The modulus measures distance. Multiplication steers and stretches vectors. The roots of unity govern absolute symmetrical balance. Algebra is, quite literally, the hidden language of spatial shapes and perfect geometric symmetry.
I'll leave you with this thought to ponder. If abstract algebra perfectly maps the visual geometry of triangles, circles, and symmetrical polygons, what other hidden, beautiful shapes are just sitting there, waiting to be discovered inside your equations? Keep exploring, and hey, thanks so much for joining me on this explainer.